Welcome back. In this slice of physics, we're going to tackle another example dealing with electric potential and potential energy as well as kinetic energy. We're going to take the example where an electron is shot towards a fixed negative charge. Now you know that an electron is negatively charged, so it'll be repelled by the other negative charge, but if it's shot towards it, it will move closer as it's slowing down. Similar to a ball being tossed up in the air, it doesn't want to go away from the earth, but it will go and get slower as it does that. We want to see how the kinetic energy and the potential energy of the electron changes as it moves towards its turnaround point. That would be the closest approach to the fixed charge before it turns back around. We will also take a look at how much the electric potential changes between its initial point and its turnaround point. And then we will use these calculations to figure out how close the electron gets to the fixed charge before it turns around. So our specific question states that an electron is shot with a speed of 3.5 times 10 to the 6 meters per second, so that's 3.5 million meters per second. Electrons can travel fast because they're light, towards a negative 10 nanocoulomb fixed charge from a distance where the electric potential is minus 5 volts. How much potential energy does the electron gain in traveling to its turnaround point, which would be the closest approach? What is the electric potential at this turnaround point, and how close does the electron get to the fixed charge? So let's start with our initial step, which would be to draw a picture. So here's my fixed charge, that's negative 10 nanocoulombs. And here's the electron. It's initially at a position where the electric potential is minus 5 volts. So let me note that down. V is minus 5 volts. You'll remember that V is used both for the unit of potential, which is volts, as well as the symbol for potential, which is written as a V. And this electron is shot towards the fixed charge with a speed of 3.5 times 10 to the 6. So I'm going to use a script VI for that, because unfortunately we got the same V being used for speed as well. So to not confuse, I'm going to use script V, and I'm going to call this the initial speed of the electron, which is 3.5 times 10 to the 6 meters per second. All right, this electron, once it is shot with that speed, is going to move towards the fixed charge, but it's going to feel a repulsive force as it's doing that. So it's going to keep slowing down, and eventually it's going to get to a point where it stops momentarily before it turns back around. So this is my turnaround point, and I'm going to call that the final point. So let's say Vf, the final speed at this point, is 0 because it momentarily stops. Now this potential of minus 5 volts at this distance was created by this fixed negative charge. We know that the potential around a negative charge is always negative, and it gets to be more negative as it gets closer to the charge. So the potential here, if I call these I'm also going to label these points as A and B. So there's A over here and B over here. And so let's call this V sub A, and this V sub B over here at this point. We'll figure out what that is a little bit later, but we expect it to be a bigger negative value or a smaller potential. So just for reference, if I show this as a graph, that negative charge of minus 10 nanocoulombs is sitting at the bottom of a valley that gets steeper as you get closer to the charge. And so its initial point of point A is over here, let's say, and point B is over here. And you'll remember from previous discussions that negative charges are like helium balloons. They like to, left to their own devices, they like to fly up. But in order to fly down, I have to force it to go down, which is why it was shot with an initial speed, and then it stops at B, and then it flies back up. As the electron moves to a lower potential, it gains potential energy. Remember that things left to their own devices will always move to a lower potential energy, and in this case, since the electron is doing something against its will, it will gain potential energy. And as it gains potential energy, it loses kinetic energy. Very similar to a ball that's being tossed up, except in this case it's more like a helium balloon that was tossed down towards the earth. All right, how do we figure all this out? So what I'd like to do is determine the change in potential energy. I think that was the first question. How much potential energy does the electron gain? So we want to find this out. And then we want to find out how much electric potential change it went through. That's the next step. And finally, we want to find out how close it got to the fixed charge. So if we call this distance x for the closest approach, we want to figure out what x is. Those are our three things that we have to do. Okay, for the first step of figuring out the change in potential energy, or the gain in potential energy, how do we do that? We have been given these initial and final speeds. The initial speed was given in the question, the final speed is implied, given that it's a turnaround point. So we know that the kinetic energy of this electron is dropping as it's flying from A to B. And we also know that this is an isolated system. Once the electron was shot, there is no work being done on it. So my external work is 0, and which means energy is conserved. Total energy change is 0, which translates to potential energy change plus kinetic energy change is 0. So if I can get kinetic energy change, I can immediately get potential energy change from that. How do I get kinetic energy change? That's simply final kinetic energy minus initial kinetic energy. And so in this case, the final kinetic energy is 0 because it comes to a momentary stop. The initial kinetic energy is 1/2 mass of the electron times the initial speed squared. Kinetic energy is 1/2 mv squared. So this works out to be 1/2 times the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms, times the square of the speed, which was 3.5 times 10 to the 6, the whole thing squared. This, your calculator will tell you, is minus 5.58 times 10 to the negative 18 joules. I'm just going to work in joules and not bother converting this to electron volts. Okay, so I've got my change in kinetic energy, which is negative, which tells me that the kinetic energy drops, which is what I expect. And from this equation now, I can get delta U. Delta U is simply minus of delta K, so a negative of negative will make it a positive, 5.58 times 10 to the negative 18 joules. So there's my answer to the first part. Switching colors, now I want to get the change in electric potential. And you'll remember the equation U equals Q times V, which last video we saw translates to delta U equals Q times delta V. And if I know delta U and Q, I can get delta V. So delta V would simply be delta U divided by Q, which is 5.58 times 10 to the negative 18 in SI units. I divide that by the charge of the electron, because that's the particle that's moving. So that's 1.6 times 10 to the negative 19 coulomb with a negative sign in the front because it's an electron. And so that'll give me minus 35 volts. Joules over coulomb is volts. So that's the change in electric potential, which I can write as VB minus VA. And since I know VA is negative 5 volts, and when I plug that into this equation and solve for VB, I will get VB is minus 40 volts. So there's my answer to the second part. And finally, we want to get this distance x, which is the closest approach. How do we do that? Well, this potential terrain was created by this fixed negative charge. And we know the equation for electric potential. That's simply V equals K times Q divided by R. So in this equation, I know the value of the constant. I know the value of the fixed charge. Now you got to be careful in this equation, since the potential terrain is created by the fixed charge, I need to use Q as the value of the fixed charge. So we know V, K, and Q, we can solve for R. So I can rearrange this equation to write R as K times Q over V, which is 9.0 times 10 to the 9 times the charge of the fixed charge, which is minus 10 times 10 to the minus 9, divided by the potential at that point, which was minus 40 volts. And when I solve for this, I will get 2.25. And since I put all of the input in SI units, this will also be in SI units. So it'll get as close as 2.25 meters before it turns back around. And by the way, if you want a little more practice, the potential at point A was already given, so you can easily figure out what the distance of point A was from the fixed charge. That's it. We're done with solving for the potential energy change, the electric potential change, and we have figured out the closest approach. So this example helped us get some more practice with electric potential and potential energy. We saw that an electron gains potential energy and loses kinetic energy as it moves towards a fixed negative charge. Then we saw that it moves to a point of lower electric potential as it gains potential energy. And we used these facts and the corresponding calculations to determine how close the electron gets to the fixed charge before turning around. Thanks for watching.